Scatterplots and regression. Let me tell you what that means. A scatter plot is something you've probably seen before. It's where you have basically a whole lot of dots and you have to make some sense of it. I'm going to give you two examples for linear and two examples for exponential. And I'm going to give sort of exaggerated examples. Linear equations obviously form a straight line. Now, in the examples we're going to do, they don't have to be perfectly straight, but they can be in a linear pattern-ish. They could have a linear tendency. It could be a positive slope or it could be a negative slope, and we've been through all that. Exponential equations, on the other hand, are going to be things that increase exponentially like this, or that might get a little too steep there at the end if you want to get technical about it. Sorry, I didn't mean for it to get that steep. Or they might decrease exponentially. That's known as exponential decay. I'm going to write a few basic things down. This is positive slope. That is if something is increasing over time, if time is one of the variables. This one would be negative slope. This one would be exponential growth, which makes sense because it's increasing. Exponential growth. And this one is exponential. The opposite of growth would be decay in this case. Okay, the biggest portion of this lesson is going to be getting used to the steps on the calculator. So if you don't have a graphing calculator, you need one. Go ahead and get one right now. And we will go through it. All the steps that you're going to need are right here in bold, and it's quite involved, but when you get the hang of them, things are going to go pretty well with it. So I'm going to do two examples down here. One of them is going to be linear, and the other one's going to be exponential. Sometimes you can look at the table and tell what it is, and sometimes you can't. So here's what we're going to do. I'm going to go through these examples while guiding you rather slowly through these steps, and it's pretty involved. And then I'm going to work through page 2 as well, and then the rest of it is up to you. So here goes. Most of what we're going to do is based on statistics, stat. So we are going to press stat. Okay, we need to edit a list. So we press enter on edit. Okay, you might have stuff entered in, you might not. If you do, you can go to the top of the list and clear it out. In mine, I don't need to clear list 1. L1 means list 1. L2 means, well, list 2. I do need to clear out list 2. Yours might be different. I'm going to press clear, and then I will press enter. And it cleared it out. Let me tell you what not to do. Do not go up here and hit delete. That deletes the entire list. Real quick, I want to show you. If I do that, then L2 is gone, and I need L2. I need L1 and L2. So I need to put it back. Don't worry about how to do that. Oops, I just did the wrong thing. And now I'm having a hard time getting it back. What have I done? I don't know. There we go. I'm having a hard time here. Man, see, and that's why you shouldn't press delete. You should clear it instead. You want to clear your list, not delete your list. Okay, we are going to type all our X's in L1 and all my Y's in L2, and so we're going to just type them straight down. -4, enter. -2, enter. 1, enter. 6, enter. 11, enter. All of our X's are in list 1, and we're going to type all these in list 2. Now, before we type, I'm just going to talk really quickly. This might be linear. It might make a line, positive or negative slope. It might be exponential, so it might increase like this, or it might have exponential decay like that. Kind of awkward with the hand going across the screen, wasn't it? And sometimes you can tell from the table, and sometimes you can't. This is one of those that's not very obvious. Maybe you could figure it out, but it's not too obvious. So what we're going to do is type in the Y's under list 2, so -8, -1, 9.5, 27, and 44.5. Pause it if you need to. And then we have completed this step right here where it said enter your x's in L1 and your y's in L2. Okay, here we are. We're on the fourth bullet here. Press second and then y equals, and that is stat plot. Second and stat plot. And we are going to go to the stat plot menu. This is our stat plot menu. We can have as many as 3 different stat plots going at a time, but generally, for our purposes, plot 2 and plot 3 need to be off, and more than likely they are. If they're not, you can turn them off. You'll know how in just a minute. Let's choose plot 1 and then turn plot 1 on. So while we're sitting here with the cursor on 1, we will press enter. And see how it's flashing on on? We're going to hit enter, and now plot 1 is on. Okay, and just let's notice a few things. This is selected, which means it's a scatter plot. The other ones would be like a box and whisker plot or a histogram or those types of things. The X is going to be L1, the Y is going to be L2, and mine's going to put a bunch of little squares on there. You'll see what I mean in just a minute. So, in just a second, we are going to find out if it's linear or if it's exponential. We need to look at our graph. If I pressed graph right now, I would not see enough of the graph, and I'm going to tell you why. Don't press what I'm about to press. Not yet. This is the window range of my graph, which means this. My x's only go from -10 to 10. The minimum is -10, the maximum is 10. However, I have an x value that's bigger than 10. My y values also go from -10 to 10, but I have y values that are outside of that range. Therefore, this window is not sufficient. Don't worry about where this window comes from. Don't worry about that right now. That's irrelevant. Here's what you do press. Here we are. Now you start following along again. Press zoom. See where my finger is on the calculator. Press zoom. And there's a long list right here, but if you go to number 9, zoom stat, it will automatically adjust the viewing window to where you can see what you need to see. There we go. So, when we pressed 9, we see this. So tell me, not like I can hear you through the computer screen, but tell me, is this linear or is it exponential? I think it's safe to say that this little guy right here is linear. So we want to choose a linear equation. All right, let me tell you what the word regression means. Regression is just a fancy way of saying I want to find the equation for a scatter plot. So we have just pressed zoom and zoom stat. We looked at the graph. We decided it's linear. We need to figure something out that is statistics based. So press stat again. And we need to calculate something. So go over to the calc menu. All right. This REG means regression. Let me show you some options. We are only going to do 2 of these right now. There is linear regression, quadratic regression, cubic regression, quartic regression, another linear regression that we're not going to use because it's confusing. This one is natural logarithm exponential regression. This is the other one we'll use, and then we get into some power regression, logistics, sinusoidal, all kinds of crazy things. Here are the 2 we need again. We will either be using linear or we will be using exponential. For this problem right here, we decided it was linear. We're going to choose linear. It's number 4. Press enter on 4. Now, don't press enter again yet. By the way, if you have a newer calculator, your screen's going to look different at this point. But for now, we'll just go with this. We'll cross that bridge if we get to it. Press enter on the regression that most closely matches the shape of the graph. Done. After you've chosen the regression you need from the calc menu, press bars. I'm going somewhere with this. Trust me. See this button right here? It says vars. That stands for variables. Press vars. We need a y variable. You can see where I'm pointing right there. We're going to go to y-vars and choose function. I know it's a lot of steps, but you'll get the hang of it, trust me. And then choose y1. and we're not going to pick Y2 right now. So we're going to press Y1. Here's what this means. The calculator is about to find the equation that matches all this data, actually all of these data, the word data is plural, and it's going to store all that equation stuff under Y1. That way I can graph it. I'm going to press enter and it's done. All right, let's figure out what all this means. Which, by the way, we're kind of done with our little bullets up here. See, we're kind of done. There's a gap here. That's what you do when you're finished, but we're not quite finished with all the statistics stuff. Okay, we're going to write down the equation of the line. Y equals AX plus B. For some reason, they don't use M, they use A. So Y equals AX plus B. M, A, same thing. This is the slope. This is the Y-intercept. They told me what A was. It's 3.5. 3.5x plus B, which in this case is 6. We just found the equation. Isn't that neat? All right. It did not ask this, but I'm going to do it anyway. I'm going to write something down. Find x when y is, oops, I said that backwards, I'm sorry. Find y when x is, I'm going to pick a random number, 21. If I want to find the y value when x is 21, it is so incredibly easy. Here's what you do. You take your calculator, and you're going to plug a 21 in for x right there. So 3.5 times 21 plus 6. So what I really have is y equals 3.5 times 21 plus 6. Boom. Y equals 79.5. I've just made a prediction. When we get to the actual real-world problems in a minute, you'll see. Okay, let's do the second one. Sitting over here, we're going to go through the same steps. We will press Stat. And we need to edit our list. So we hit enter on edit. We still have the data in there from a minute ago. And if you want to, you could type over top of it. Oops, I messed up. 0, 1, 2, 3, 4. You can type over the top of it. That's fine. If you wanted to, you could go up to the top of the list and press clear and then enter. That'll work as well. The danger, though, is if I type these things and then I get to a problem that has less things, then I'm left with some old data dangling around down here. So it's a good idea to clear it, or at least make sure you've typed over everything and deleted what's left. Okay, I wonder if this is linear or exponential. Actually, let's kind of look at it. I'm increasing by 1 here. I'm increasing by 1.5 here. I'm increasing by 2 1/4 here, and then I'm not increasing by a constant amount, so I'm not adding the same thing every time as I go up. I'm probably multiplying by the same thing, which makes it exponential. But let me prove it to you. Okay, the stat plot is already on. Remember a minute ago when we hit second and stat plot? And we had to turn that on. Well, it's already on. We just did a problem that needed this to be on, so it's still on. So all we need to do now is look at our graph. Let me go back to the steps for just a second. We're right here where it says press zoom and then zoom stat. That's going to let us see the graph. So zoom and scroll down if you want, but I'll go ahead and tell you it's number 9, and that automatically does it. All right. Mr. Reader, what's that? Thank you for asking. This is left over from the very last problem that we did. Remember when we had Y1 in there? We could have pressed graph and it would have shown the line going through those points. I forgot to do that. I'm sorry. What I'm going to do is press Y1 and clear that out. See that? There's your equation from a minute ago. Remember? Okay. So we look at this and we have to decide, is this linear or is it exponential? We already know what it is. It's exponential. We discussed it when we were looking at the data. Nevertheless, we can look up here and decide, hey, that's got a little bit of a curve to it. That's exponential. That's not always the case, but in this case, it is. It's a pretty good curve. Now, not every exponential data set is going to be perfect. Not every linear data set is going to be perfect. Some of them are going to be kind of scattered and hard to tell. So, here goes. We're going to press Stat and go over to Calculate. We want to calculate a exponential regression. It's letter 0, number 0. And you press Enter. Before you go any further, we want to save this as y1. So we're going to press vars and go to yvars and then enter on function and press enter on y1. Okay? Enter again and it's saved in there. Okay, when we talked about exponential equations, we said that they are of this form right here. Had an accent that kicked in there out of nowhere. A times b to the x. They didn't use parentheses in this, but it's the same idea. Where a is 2 in this case, and b is 1.5, which actually means it's increasing by 50% every time. There we go. That's it. We found it. Let me show you something cool. You know, a second ago when we pressed vars and went to yvars and saved it under y1, if you press y1 or y equals, it's saved under there, and that means this. If you pressed graph right now, not only do you see your points, you see your equation going through it. You see your regression equation. And that tells me that this hits all the points and it's a really good fit. Let me show you something kind of neat. Just kind of ramble a little bit. Let's suppose that I didn't know if it was exponential or linear. All right, so here's what we did. We plotted our points. You don't have to press buttons, just watch. We did all that stuff, we typed it all in, we did our thing, and we looked at the graph and we were like, I guess it's exponential, I don't know. And so then we typed all that mess in and we got this. And we said, I wonder if it's linear. I wonder if I was wrong and it was linear. Maybe it's one of those that's really hard to tell. So I'm going to press Stat and go to Calc, and let's do linear as well. And when I do that, I'm going to save this one not under y1 but under y2, and that way I'll be able to compare them. So I just pressed vars. You don't have to do this, but just watch. Vars, go over to yvars and hit enter on function. I can save it under y2 instead. Now check this out. This is the linear equation that fits it. When I press graph, it's going to show you the data set. It's going to show you y1, which I decided was exponential, and it's going to show you y2, which was linear. Which one fits it better? Exponential or linear? There will be questions that you will encounter, more than likely, that will say, what is the best model of this data? What's the best equation that fits this data? And you have to decide if it's exponential or linear, and this is how you tell. Now, there are other ways to tell. They're not always that accurate, but often, visually, it's a great way to tell. Look and see how closely it matches the pattern. Exponential matches better than linear. Now, this one was a little more obvious. Let's go back to this for a second and make up a real quick question. If it said find y when x is 5, this is really easy. All we got to do is y equals 2 times 1.5 to the 5th. And y equals 2 to, oops, about wrote the same thing again. How about I just type it in? Let's quit and quit the graph. And we can just go 2 times 1.5 to the 5th. There is a way to do this in the calculator, by the way, in a different way. I'm not going to go there right now, though, because the fact that we have it stored under y equals will kind of help us out in the future, possibly, but we're not going to go there right now. This is a little overwhelming as it is. Okay, there we go. There's the first page. And I'm going to stop the video here, and I'm going to resume with the second page. That'll be the second video, and then the rest of it is on your own. In the previous video, we did the first page. And now we're going to start the second page. Real quick, before I do that, though, I'm going to write some stuff down that'll come in handy. Linear equation, y equals mx plus b. Yes, I wrote a instead of m. You know what this is. This is your slope. That is also known as your rate of change. I'm going to write it one more way, and I'll just keep putting it in parentheses. This is change in y divided by change in x. That'll come in handy in a minute. And this is your y-intercept. And to put it in a different form, this is the y value when x equals 0. That's your starting point. All right, let's hit this one. Y equals a times b to the x, and this is stuff you've seen. This is your initial value, also known as your starting point. So, initial value. Let's reword this a little bit. This is also the y-intercept. And to steal a phrase from over here, this is the y value when x equals 0. What's this? This is the growth or decay factor. This is what I'm multiplying by every time. Or, well, I almost said dividing by, but we can multiply by a fraction. Okay, knowing that, that's going to help us answer some of the questions on the second page. So let's do it. Pause it if you need to, but I'm going to flip the paper to the second page, starting now. Okay, table below represents the results of each U.S. census since 1920. When we read the directions on number 1, it tells us to determine if it's linear or exponential by graphing it, but it also says, don't type all that in. It does tell us that's L1, that's L2. You don't need the years, not in the calculator. So here we go. This is L1, this is L2. Let's type. I'm going to go really fast. Stat, edit, and I'm going to clear my lists. 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. There we go. And then we'll type L2. There we go. It's all in there. You can pause it if you need to, but I'm going to keep on trucking. Our scatter plot is on. You don't have to press what I'm pressing, but I'm just proving that it's on. And we want to see what this thing looks like. So zoom. I can scroll down to 9 if I want to waste my time, or I can just press 9 because that's zoom stat. Okay, see that random thing floating around right there? That's left over from the last problem. It probably is to our benefit to get that and that out of the way. So sometimes these things are left over. They're clouding my view. Press Y equals and clear both of them. There we go. They're gone now. And we can press graph again. Okay, so now the question is it linear or exponential? And we don't know. We don't know. So we're going to try both of them and see which one fits better. I'm gonna just scribble over here on the side. I'm gonna let L1 be linear. I'm gonna let L2 be exponential, and then we'll compare and we'll see which one fits better. All right, we kind of have to watch it in the order that it graphs it as well. So stat, I want to calculate something. I want to calculate a linear regression. Press enter on that. Now before I go any further, before I do anything else, I need to press vars and save it under yvars, function y1, enter. There we go. I'm going to just write it down here on the side. I like 2 decimal places. Not everything in life turns out neat and pretty. We have to round things off sometimes. So 2.28x plus 93.16. So that's the linear equation. Now we're going to do the exponential equation, and we're going to save it in L2. So stat, go over to calc. It's number 0. If you want to press 0, you can, but I'm going to scroll down to it. Exponential. Press enter. Go to vars. We're going to save it under yvars, and it's a function. Now don't put it under y1. y1 is the linear one. We're going to put it under y2. Takes it a minute. Y equals 107.24, rounding it off, parentheses, 1.01 to the x, random statement here. The more decimals you carry here, the more accurate predictions will be. Just saying. Okay, so that's what we have. I'm about to press graph. When we press graph, we're going to be watching it as it graphs so we can see which one is better. So, graph. This is linear. It's all right. This is exponential. Okay, you want my guess? You want what I think? I think exponential is better, and here's why I think that. Two reasons. First of all, the exponential one kind of swung around here. It's kind of hard to tell, but it seemed to hit more dots or hit them more closely. Linear just sort of cut through and had a few over here and a few over there and a few over here, and it didn't really follow the pattern as well. So again, this one right here was linear. This one was exponential. I think exponential is better. Here's another reason. This is the real reason I feel this way. The exponential equation more closely predicts population. Population generally is a exponential thing because population increases like this. There are exceptions to that, of course. So we found it. We decided it was exponential, and we were going to write the equation, which we actually already did up here, but I'm going to put it in the correct place. So 107.24 and then 1.01 to the x. All right. Within the context of this situation, what does the a value represent in your equation? Well, first of all, this is the a value, and let's slide this paper back. I'm on the first page again. Now yours is front and back, mine's not. A is the initial value. It's the y-intercept. It's the y value when x equals 0. It's the initial value, and so what it means here is I started at 107.24 million people. Now, I know I really started at 106, so this is an approximation, and it's a little bit off because real-world data is not very pretty. We get used to things being in nice straight lines or beautiful curves, and this is not. This is real-world population. So like in these couple decades, we had war and depression, and that affects population change. It does. There was a baby boom that happened right about in here, and there was a huge explosion in the population. It happens. There were changes in things. So it's not going to be a necessarily exact number. We know how it started, but this is the prediction of how it started. So it's not perfect. Within the context of it, what does A represent? 107.24 is an approximation of the initial value, and it's an approximation of the initial value, and the initial value really was the census in 1920. That's as far back as we went. So I'll just leave it there. Number 3, within the context of the situation, what does the B value represent? The B in an exponential equation is the growth or decay factor. So let's be realistic. So if I have 1.01, then I have 101% growth factor. And it's growth because it's going up. Population most of the time is increasing. 101% growth factor. If you want to get technical, it's a 1% growth rate. We won't go there right now. Use your equation to predict the U.S. population for 2020. Well, 2020 is, now don't plug in 2020 for X now. 2020 is right here. That is 100 years after 1920. So what we are going to do is plug in a 100 right there. Don't plug in 2020 there. Don't plug in the year. Plug in the number of years since we started there. So we're going to go y equals 107.24 and then 1.01 to the 100. So let's do it. Let's quit out of the graph. And we're going to go 107.24, 1.01 to the 100. There we go. About 290.06 million. Is it accurate? Actually, no. This is an underestimate. I want you to notice something here. This is used to approximate things. We have to be careful with this. But 290 million in 2020? Oh no. We've already passed that. So we're more than likely going to pass that in the year 2020. Okay, let's do the next 4 problems much quicker, and then you're on your own for page 3 and 4. The data in the table represent, it sounds like bad grammar, but again, data is plural, so the data they represent U.S. health expenditure on medicine by year. Let's press Stat, hit Enter on Edit, and we're going to clear these lists out. Go up and clear and enter. I'm going to go really fast on this. You can pause it if you need to catch up. For the year, I'm going to do something that we used to do back in the 20th century, and you don't remember. We would take off the 19s, and we're going to do this. We are not Y2K compliant. You probably don't get that, but that's okay. You weren't around in the year 2000, or don't remember it if you were. Okay, so we're just going to do that right there. So we're going to put 95, 96, 97, and 98, and then we come over here and we go 8.9, 9.4, 10, and 10.6. There we go. And I want to see what this looks like. I want to see if it's linear or exponential. My scatter plot is on. I can press that and waste my time if I want to, but I choose not to, even though I just did. Press zoom and zoom standard. I pressed the wrong button. My bad. I just said that out of habit. Don't press zoom standard. When you press zoom standard, it takes you back to the window I was telling you earlier. -10 to 10 and -10 to 10. My bad. I'm sorry. Zoom 9. There we go. Isn't that nice? Okay. Now, in case you wonder why it's still thinking, that thing means it's thinking. What it's doing is actually graphing those other 2 lines that you just did. So y equals, remember the linear and the exponential, you can clear those out and press graph. Okay, what do you think? Linear or exponential? I'm pretty sure this is linear. Now, it's got a little tick right here that makes it look like it's about to curve up a little bit, but I don't think that's enough for us to worry about. I'm going to say it's linear, and I'm not even going to explore exponential now. If I wanted to, I could, but I choose not to. So, I say it's linear, and I'm going to write the regression equation, and I need to calculate it. Stat, calc, linear regression. And I'm going to store it under Y1, so press vars. Why am I doing that? So I can really look at it and make sure it fits. I'm going to hit enter on function and enter on Y1, and there it goes. Let's go ahead and write it out. Y equals 0.57x minus 4528. Okay. So there we go. We've got number 5. Number 6. Actually, before we go any further, let's press graph. I just want to show that to you. Isn't that neat? That looks like a pretty good fit to me. Exponential with this few points would really not help too much. I'm sure it's not exponential. And by the way, the slope is not consistent. Let me point this out too. From here to here, you went up by 0.5. From here to here, you went up by 0.6. From here to here, you went up by 0.6. So it's not a consistent addition every time. Within the context of the situation, what does the A value represent in your equation? Well, it is linear, and the A value is what used to be called the M value and the other stuff. It's the rate of change. It's the change in Y over the change in X. Let me put that in good plain English for you. It is the number, it's the change in expenditures per year. It's Y per X. So it is a 0.57 billion, I got that from that right there, dollar increase per year, because it was going up per year. Within the context of the situation, what does the B value represent? All right, this is about to get tricky. B is the Y-intercept, and if you want to write Y-intercept, that's sort of not completely accurate. Yes, it's the Y-intercept, but it's the Y value when X equals 0. Okay, if X was 0 right here, what would it be? I'll go ahead and tell you what it'd be. It would be the year 1900. That's what it would be. None of us were around then. Within the context situation, what does the B value represent in your equation? It is the expenditures in the year 1900. It is when my X value is 0. Now, it is not realistic, because that would be a negative amount of expenditure on on medicine. In 1900, they spent more than negative $45 billion. I mean, that's a negative amount. That doesn't even make sense. Using your equation, how much money do you think was spent on medicine in 1999? Let's do it. Y equals 0.57 times what? You better not say 1999. It's just 99. Minus 45.28. We use this to make predictions. Ignore that page number right there. We're going to quit out of our graph, and we go 0.57 times 99 minus 45.28, and there we go. 11.15. Let's put some words with it so we know what it means. $1 billion. I'll put a symbol in a word. There we go. That's how much was spent on medicine in 99 based on our prediction. Okay, the rest of it's up to you.